So just for questions, if you raise your hand, we try to get the mic to you after the talk. So let's get to real world. After Mona Lisa Neuron, let's go to wireless world from Qualcomm. We are honored to have Dr. Karam Chatha. He is Senior Director of Engineering Corporate R&D from Qualcomm, and the title will be on mobile devices and AI, basically real-world products for computing, AI computing at the edge on the mobile devices. It's my pleasure to introduce Dr. Chatha. He is a Senior Director of Engineering at Qualcomm, and he leads specifically the SoC architecture research design team. Karam has been with Qualcomm for about 5 years. And before joining Qualcomm, he was a tenured associate professor at Arizona State University. I mean, he joined industry from academia. We have actually, I think, 2 more speakers on the software side who went from academia, from their, they were professors and they went to industry to, I think, Amazon and Google. We have them tomorrow. And actually, one of the questions about labeling data is going to be addressed again tomorrow in the software session. He has published as a professor for over 60 conference and journal publications. He's been a general chair for NOCS 2013 and ISWeek 2014, and has won numerous awards, including Academic Award, NSF Career Award. With that, please join me in welcoming Dr. Chatha. Thank you.
Thank you for the introduction. Good afternoon, everyone. So thank you, Dr. Rabai, to set the stage of what we are looking at in this field, what will be emerging in the next few years. What I'm here to talk about is what we as Qualcomm are looking at right now at computing on the edge. So we are essentially, the talk is called AI at the Edge. And what I'm going to do is try and walk you through what are some of the challenges that we are facing today in order to bring AI to the edge, and then what are some of the approaches that we are adopting, and where we are, what are some of the solutions that we have come up with. So what I intend to do with this talk is to sort of give you a sense of what Qualcomm's thought process is in this space. So a few motherhood and apple pie sort of slides. Right? So devices and machines and things are becoming more and more intelligent. Today, for example, you have wearable devices that are smart. You have thermostats that are smart. You certainly have smart speakers. You're carrying a very smart device in your pocket right now. Right? And on and on. This is what the future looks like. It is projected by 2021 there will be 24 billion embedded and connected devices, and about half of them, so about 10 billion or so annually, will be using AI, will support AI processing. So extremely large number of devices that are going to be smart out there. And then the challenge, you can sort of begin to understand what are some of the issues that one will have to walk through. Professor Rabai sort of hinted at it in the context of the brain, that you have different subsystems in the brain that become active at certain times to perform a certain function. The same thing will hold true, certainly holds true right now on our SoCs. So we have different subsystems, and those subsystems are specialized to perform certain functionality in the most power efficient manner. So it essentially is heterogeneous compute. And this heterogeneous computing holds a secret to enabling AI at the edge. So mobile drives innovations at the edge. If you sort of look at the devices that are emerging at the edge, and if you sort of talk about smart homes, industrial IoT, wearables, a lot of the problems that you are going to address in that space, we have already seen in the mobile platform. Right? You have to worry about extremely low power consumption, extended battery life, making sure that the thermal limits are honored. Right? You don't want your watch to be heating up. and so on and so forth. And these are many of the technologies that we have mastered within Qualcomm, and then we are basically transitioning them and applying them to enable devices on the edge. Of all the slides, I think, of all the slides that I'm showing you, this is the one which I really like, quite frankly. Because this one is mind-boggling. I mean, I've seen it a few times. It's still mind-boggling, right? But between 2017 and 2021, there will be about 8.5 billion shipments of mobile platform. It is the largest distributed computing platform ever deployed by mankind. And then you can sort of take it from there and to figure out what is the potential that it holds, right? Each one of us here today is carrying a cell phone in our pocket. And, we are 300 of us here, I believe. That was the number that was told. And that's a fair amount of processing power that's right here, right? And then you take it across the world, and then you sort of try to figure out what can you do with this. And the possibilities are endless, actually. So now let's start talking a little bit about deep learning and how, what it means in terms of the edge. So learning, or machine learning, deep learning, has been primarily on the cloud. So training, you have these deep networks, you're trained. The training happens always on the cloud, right? And then now you're beginning to see, earlier on, inference would also happen on the cloud, but now you're seeing a steady migration of what inference happening on the edge. And the primary reasons for enabling inference on the edge is basically low latencies. You don't need to go back to the cloud in order to get your inference done. You are preserving privacy, so you're not sending your information back to the cloud. Reliability, right? You're not subject to coverage, your cell phone coverage that may or may not be there. So in all sorts of places, we are seeing inference, primarily inference, migrating towards the edge. So certainly on the in the mobile handsets, on the drones. I don't know if you've seen our CES demos where we have drones which are flying and which are doing classifications as they are flying. Certainly in the automotive space and on the wearables. So as I mentioned, on-device intelligence is necessary, right? I mean, you cannot have inference or intelligence just confined to the cloud. That's too limiting. We live, if you're going to take advantage of this large distributed, really large distributed computing platform that is out there, you really need to bring AI to the edge. And as I mentioned, it gives you advantages in low latency, privacy, reliability. So what are some of the challenges that one needs to overcome in order to bring AI to the edge, right? So a little bit about these workloads. So if you are conversant with deep learning workloads, they are extremely computationally heavy. I'll give you some numbers of how many gigaflops you need in order to do one inference through a particular network, right? So this is a kind of workload that pushes the limit on every processor that is out there. It pushes the limit on processors that are in the cloud, and certainly pushes the limits on processors that are on the handset. So they are extremely compute intensive. The other challenge with this workload is, I mean, in some ways, this workload is a computer architect's delight, actually. It pushes you on compute. It also pushes you on memory bandwidth. So this workload takes a large amount of data. It's a model. It takes weights. The weights run into several megabytes of data. Typically, in some of the large models, it's up to 100 megabytes of data. And you cannot obviously store it on the chip. So it has to be resident in the DDR. And then you have to worry about, you're doing large amount of computation. You want quick inference times. And you have to move several megabytes of data in and out of your DDR on a mobile platform, right? So you begin to see some of the challenges that will arise. You really need to worry about how efficient are you doing the computation, how efficient are you in moving the data from various memory structures that you have. So power is key, which ensures longer battery life. Thermal is key, so which ensures really useful applications. You don't want your phone overheating. You don't want your watch overheating. You don't want your headset overheating. And you, like as I mentioned, you need to worry about memory and bandwidth limitations. So a little bit about the challenges that we face. The power requirements in this domain, when you're talking about computing on the edge, if you sort of looked at all the slides that I had, on the slides that I had, they vary. The power limits are not the same as they vary from what is the power limit on your headset to what's the power limit on your watch to what's the power limit on your mobile device. So in the variable space, it's milliwatts of power. So about less than 1 milliwatt for an always-on sort of scenario to up to 50 milliwatts when that variable device is functioning at full capacity. In mobile phones, you have a slightly larger battery, so you have 10 milliwatts in the always-on and somewhere around 1.5 watts in bursts that you have to be able to sustain. Technology scaling certainly helps. Going from 14 nanometer to 10 nanometer gives you about 15% of saving, right? It's non-trivial, but it is not nearly as much as what we used to get earlier. Then power gating further reduces power. So again, going back to, I'll show you the sort of a top-level diagram of what our chips look like, but certainly there are multiple subsystems in the chip. Each subsystem is specialized to do certain tasks in a power-efficient manner, and you only power on the subsystem that you require. Right? So if your camera is on, right, and you are not, if your camera is on, your modem does not need to be doing as heavy a processing, right? If you are not really rendering, then your GPU need not be switched on. It should be switched off, right? So power gating certainly helps. DVFS, or dynamic voltage frequency scaling, also certainly helps. And these are classical techniques that one uses in order to sort of overcome the power consumption challenge. But there are other challenges that remain. Power density and thermal is a huge challenge, right? It goes back to how heavy this workload is in terms of computation. So it really pushes the limits on what you can sustain thermally on a handset. The other challenge is this fast switching, DI/DT challenge that happens when you switch on all of these transistors all of a sudden, right? And your power supply is not able to sustain the current that, you get voltage droops on your power supply. And you have to worry about it. So then what needs to happen is you cannot switch on and switch off instantly. You basically have to have a gradual switching on process and a gradual turning down process. And then you need to, here's the other kicker, you need to really anticipate when you're about to switch off, right? Because if you can do that, you can be efficient you can extend your battery life because you can be more efficient in switching off your subsystems. And then you need to really worry about the DDR bandwidth. So DDR bandwidth is critical. I mean, first of all, it's always, based on the concurrent applications that you're running, the DDR bandwidth is a scarce resource. But perhaps more importantly, DDR power is something that you want to avoid. So you really need to be careful about how much power you're consuming in your DDR. So how does your computation move data in and out of your memory? So ideally, what you want to do is, if you're doing, for example, a deep learning network, you get your weights out of your DDR once into your local memory, perform as many computations as you can with it, and then get the next set of weights, and you're not getting the same set of weights again and again. Sometimes it's possible. Many times it's not possible. So you need to worry about what is the sequence in which you perform your computation such that you can minimize your DDR power consumption. So in order to address this challenge of bringing AI to the edge, it really is going to take, it's going to take everything that we got, right? We do need to look at it from an algorithmic standpoint. The same networks that we were using for inference in the cloud don't necessarily apply to the edge, right? These need to be modified. And I'll talk a little bit about some of the modifications that folks have looked at, right? So certainly you need algorithmic advancements. Couple the algorithmic advancements with the architecture innovations or efficient hardware that can basically support this high intensity workload. The key, as I mentioned, is you do need heterogeneous compute. Not all networks will work in fixed point domains. Some definitely require floating point architectures. You will run into scenarios where there's an application that requires what we call hierarchical computation. So in other words, it's an always-on scenario, extremely low power, and there's a network that's running, right, which is trying to detect perhaps a keyword, right? Once the network says, this might be a keyword, then it goes ahead and wakes up the other parts of the subsystem, which does the more, make sure that it was indeed a keyword, not a false positive, and then does the next set of computations. So in that sense, what you need is certainly hardware, which is an application. So what I described to you is an application that is across a heterogeneous subsystem. From an extremely low power subsystem to perhaps a more performance and power intensive subsystem. And you need to be able to manage that heterogeneous subsystem. And then the moment you have heterogeneity on your chip, if you want to effectively be able to exploit all that's available on the chip, you better have the software to back it up. Without the software, the hardware doesn't go very far. Right? So we can put as many GPUs and CPUs and the DSPs, and you'll see those on a follow-on slides. But I do need a software layer sitting on top, which is able to facilitate that distribution of tasks across all of them. And I'll talk a little bit in the context of what we have within Qualcomm for deep learning. So we are essentially looking at scaling performance from somewhere 2 orders to 3 orders of where we are right now. We would like to reduce model size, right? So I'll talk a little bit about model size reduction. That will reduce your memory capacity and memory bandwidth. Pruning and quantization are effective approaches to do so. We want to reduce the computational complexity, so we want to make those networks more efficient. There's a lot of redundancy in these networks. Again, I'll give you some data to sort of that points to it. We do want to do joint hardware and algorithm optimization. So one way you can do it is, Dr. Rabai hinted at, so if you support 4-bit computation on your processor, perhaps you should be training the network with 4-bit weights, right? It's much more easier to do that rather than train the network in floating point and then try to shoehorn it onto a 4-bit architecture. It can be done, but a better approach would be that if you're training, while you're training, you're cognizant of the hardware that you're going to be mapping it on. Certainly new effective memory and computational logic design, and then you need the software top-down abstraction to be able to exploit all of that. So let me talk a little bit about the algorithm approaches that the trends that one is seeing. I apologize for the small font on the bottom of the slide, but I'll walk you through it. So what I'm showing you on the x-axis are different DNNs that have been proposed over the years. These are mostly from the ImageNet competition. If you are familiar with ImageNet, this is held every year. AlexNet was the winner back in 2012, which really started this whole trend about looking at DNNs. The blue bar there shows the number of layers, which acts as, which is a good indication of how much computation, how many operations do you need to do per inference. So if you look, and then the top 5% accuracy, top 5% error is shown on the bottom row. So as we go from left to right till the tall GoogleNet V4 bar, the number of layers increase. So on the left they are about 8, on the right they are about 150. The top 5% error drops from 18.2 to 4.8, right? So in some ways, having large number of layers certainly helps improve the accuracy, right? But then this was the thing about the ImageNet competition, which you should be aware of. It's really, the computation, the inference is performed on server class GPUs, right? you can't necessarily take the same network and hope to apply it on a mobile platform and be able to achieve, and still be able to do it in low power. So in the last few years, we have seen mobile net approach, or maybe it was earlier this year, and that, if you look at the blue bar on mobile net, that's the second last bar on the right-hand side over there. It's much smaller. It has only 28 layers. It's the amount of computation that you do is about it's an order of magnitude lower than what you do on the Google Net v4. The accuracy, the top 5% error is about 2x. So about an order of magnitude reduction in computation for going from 5% to 10% error. That seems like a good trade-off. There is NASNet, which brought down the error from 10.5 to 8.5. So we are beginning to see networks emerging that are taking inference from the cloud onto the edge. And these networks are essentially being designed keeping the computation capacity, the power consumption constraints of the edge into mind. So that was the layers sort of are an indication of how much computation you need to do. In this slide, I'm showing you the model size in megabytes. As I mentioned, several of these networks, especially the later ones which have the highest accuracy, such as ResNet and GoogleNet, they require hundreds of megabytes of storage. Now, it's not the challenge that you can't have hundreds of megabytes of storage on your phone. The challenge is that for one inference, you have to move that data into onto your chip, perform the computation, and then produce the result. And if you are talking about doing 100 to 200 to 300 inferences per second, suddenly your DDR bandwidth explodes, right? And the bandwidth explodes, and your power consumption goes through the roof, right? So obviously, again, if you look at MobileNet and NASNet, as they are aimed at computing on the edge, they have much smaller memory requirements. So MobileNet has about, they're of the same order, about 20 megabytes of storage. And which is tolerable, which is certainly tolerable in the mobile context. So what is some of the other approaches that folks are doing? So quantization is we have talked about, okay, don't do the computation floating point, use 8-bit or 16-bit, but one can go a little bit further. So this is a paper from earlier this year by Ulrich et al. At ICLR 2017, and they do quantization and pruning in the same step. So what they do is they take a floating point network which has been trained in 32-bit floating point, and then they apply a retraining procedure. And what they do during retraining is categorize the weights into K categories. So the K could be 16, K could be 32. You limit the number of categories. Now, so what does that mean? Well, certainly a 32-bit floating point weight, I can represent it by log 16 to the base 2. That means by 4 bits. So what you do is, now the weight is represented as 4 bits. You get 4 bits from your DDR. You have a table lookup inside your processor that converts those 4 bits to the 32-bit floating point value that you require. You perform your computation, and you have essentially achieved DDR bandwidth savings. So you could go further. There is the XNOR network, which can binarize both weights and inputs. And convolution, when you're doing convolution by binary dot product, you essentially have to do an XNOR operation followed by bit counting. So what I show in this table here is on the top row is standard convolution, and to the the rightmost column shows you the accuracy. The middle row is when you use real value as inputs, but you have binary weights. Right? So when you do have binary weights, you get a memory savings of about 32x. Your computation saving is not as much, 2x. Actually, the accuracy is about comparable to what you would have with AlexNet. And then you go to binary weights, where you have binary inputs and binary weights. You do the XNOR and Bitcoin. You have 32x reduction in memory, and you have about 58x reduction in computation. That's massive, right? But of course, your accuracy now drops to 44%. So where would this be useful? Well, this is where the hierarchical computing that I was referring to comes into the picture. You could use this for a low accuracy, always on sort of a network, right? Use this, and once you detect a significant event, you wake up the higher performing, higher power subsystem on your chip, and then that will validate that will validate or invalidate what the low power subsystem did. So you basically are, you can look at it as you're essentially duty cycling your high performing subsystem. So this one acts as a gate, right? It certainly, the accuracy is not very high, but you still you have tremendous power savings if you're able to do so. Now, if you look at DNN computation, all that I talked about is certainly valid, but the classical problems don't necessarily go away, right? At the end of the day, we are talking about matrix multiplication. So if you're going to map matrix multiplication onto a processor, certainly the classical algorithms are important. Strassen's algorithm, Vinograd 2D, which reduces the number of multiplications that you do, and that also helps with performance. You can do convolution in the FFT domain. That certainly helps with, depending upon the size of the kernel that you're operating with, that can seem beneficial too. And certainly if you're looking at a TPU sort of an architecture, then mapping your algorithm onto the 2D array sort of architecture, looking at communication costs when you're mapping onto a 2D array architecture, because communication costs have a direct correlation with how much power you're spending on your chip. That becomes important. This is a little bit about training on the edge. So this is a paper that was from arXiv from earlier this year. It's called the reversible residual net. So one of the biggest challenges with training is that when you're doing training, you use the backpropagation algorithm, but when you're doing classical backpropagation algorithm on a classical network, you need to store what are called activations or outputs of each one of those intermediate layers. And because you need to do so, you sort of think about it. What it means is if you're going to you're going to attempt to do training on the device, you again have a memory explosion problem at your hand. So what this paper does is they propose what they call a reversible residual network. And in the reversible residual network, they only need to store the activations of one layer, and they can produce the activations of the predecessor layer by computation on that one layer. So essentially what happens is your memory, if L is the number of layers, it goes down, the storage capacity goes down from order of L to order of 1. But yes, it does increase your computational complexity to 3L. And that seems promising, that if I can minimize my memory bandwidth in this manner, then certainly I can hope to do training on the edge. So now so if my talk is in some ways, I was talking about algorithm approaches that we are looking at, and certainly now let's talk about a little bit about hardware approaches. So this is what a typical mobile SoC looks like, right? We have CPUs, multi-core CPUs in there. We have GPUs. We have hardware accelerators. We have DSPs. We have connectivity, read modem. We have video processing unit, image, display, audio. It's really a heterogeneous system. Each one of those subsystems is specialized to do a particular functionality well, right? It is not as if we have one centralized core that is handling everything. That's not the model here, right? It's a distributed heterogeneous system. Each subsystem is based on the application that's being done. A particular subsystem is woken up and operated at the optimal voltage and frequency point such that the battery life can be maximized. So I'm going to talk about one of these subsystems that is in there, which is the hexagon DSP with vector extensions. So what the hexagon DSP is, essentially the vector extensions are fixed point extensions. So you can do 16-bit and 8-bit math on them, and therefore certainly suitable, very suitable for doing inference on the edge. It was introduced at Hot Chips 2015, so if you want more details about the processor, you can get it from that presentation or send me an email. So it is a classical VLIW processor. There's a scalar portion and there is a vector portion. The scalar portion has shared L1, L2, and 64-bit registers. The wide vector lanes have 1024-bit vector registers. It can do vector matrix math, MAC operations, which are multiply, accumulate, or fuse, multiply, accumulate, shift, permute, and it is served by a separate cache ports. Now, the key thing to realize here is that when you're doing AI on the edge, it is not just the AI workload that you have to worry about. There's a lot of pre-processing and a lot of post-processing that happens. So for example, you may capture an image from the camera, you will do pre-processing, you may do scaling on it before you feed it to the network. And you need an efficient engine that is able to do all the pre-processing and the post-processing that is required for your neural network. So these are some of the functionality that is supported on the DSP. Certainly video playback. If you're talking about an augmented reality or virtual reality sort of an application, you would be doing your 6DoF on the DSP at the same time as you would be doing your neural network on the DSP. Camera snapshot enhancement. You've seen style transfers that are common these days. These would be done on the DSP. Video capture enhancement and computer vision, and then certainly all of machine learning, which includes, which primarily these days includes CNN and LSTMs. So what I'm showing you here is a video. So on the left-hand side, you have the same application that is running on the CORD CPU. On the right-hand side, that application is running on the Hexagon DSP. This was, the original application was from Google. It is on a Pixel phone, and it was showcased by Google at the TensorFlow Developer Summit. And the key point here is that you get about a 10x performance improvement in frames per second at about a 50% reduction in power consumption. So there is about a 20x performance per watt differential between doing the computation on the CPU and doing the computation on the DSP. All right, so let me talk a little bit about the software aspect. So I'm going to gently migrate towards the software aspect. So if anyone of you has dealt with vector machines, there is a challenge associated with vectorization. Halide is a language that came out of MIT. It's a DSL for domain-specific language for image processing and computation photography. The good thing about Halide is that it has an algorithm portion and a schedule portion. So it has basically two major computations. The algorithm portion is architecture agnostic. So you describe what you do, what is the computation you do on one pixel, right? The schedule portion is where you do mapping of that algorithm or the specialization onto the specific architecture. What that helps you with is portability, right? You describe the application once, and what you're really going to worry about is how the schedule as you take it from one engine to the next. It also is extremely efficient if you're going to be writing certainly image and computational photography applications is extremely efficient. I'll show you an example of the lines of code that are required. And it certainly works very well for CNNs too. So on the right-hand side, I'm actually showing you the C code that one would write in order to optimize a CNN computation on a vector machine. So it's heavily using the wide vector intrinsics, and that's what you would end up writing. And on the left-hand side is the same code written in Halide. So extremely efficient. So from a software productivity standpoint, it's extremely efficient to do the computation, to write up the program in Halide. The Halide version has 14 lines versus up to 120 lines on the C side. But perhaps more importantly, it's the restructuring that the sort of optimization that one can do based on which processor you're targeting. So if you're going to be targeting a DSP with fewer number of vectors, then vector width, then you can basically change the schedule section without messing the algorithm section. And if you want to do the same thing on the C side, that becomes extremely difficult. So that's where the power of Halide comes from. This is Snapdragon 820 is what we was the chip, what was the demo that I was showing earlier. On Inception v3, it can do roughly about 100 we can deliver about 100 gigamax per second at 17 inferences per second. Our next generation design is roughly 3x the processing. There's an upping of clock frequency to 50% more with 2x the vector width, and we should be able to give 51 inferences per second on the Google Net V3. The advantage, so we are not just increasing the amount of horsepower on the DSP and then the clock frequency. We are also looking at, we are tweaking the memory hierarchy that we have and looking at low latency memories and just the low latency memories. So this speed up I'm showing you on various video processing modules, that speed up is just based on the impact of the embedded low latency memory and no increase or computation elements, so no impact of frequency increase or increased computational elements. So just by doing architecture innovations on the memory, we can deliver somewhere around 1.5x to 3x performance improvement. So the machine, so if you look at them, you have a sense of what needs to be done in order to be supporting AI on the edge. You certainly need to increase your on-chip memory for storage of weights and working memory. You need to increase that memory in an effective manner. So by that, what I mean is you don't necessarily need to want to do a large memory increase in one subsystem that the other subsystem cannot exploit, right? So you want to do it in a holistic manner. Perhaps increase the amount of cache that is available and that is shared across all the cores so that they can all exploit that. Certainly power efficient arithmetic unit with variable precision. Compression and sparsity are extremely important. Compression is important from reducing your DDR power consumption. Sparsity is important in terms of effectively utilizing your multipliers. So if you have a multiplication with a zero, which happens often in deep convolution neural networks, especially those ones which you use what is called a ReLU nonlinear function. These are extremely sparse, and what you want to be able to do is instead of doing a multiplication with zero, at the first order, certainly power gate your multiplier such that you're not paying any power penalties. But as a second order, what you want to be able to do is exploit that slot to do another multiplication, which is required. So in other words, improve the utilization of your architecture. New memory structures certainly help. And then software workflow is extremely important as we are really looking at a heterogeneous platform. So my last few slides are focused on software. So what's the heterogeneous computation challenge for machine learning? So there is dynamic scheduling of tasks that needs to be done across the CPU, GPU, the DSP, and the hardware accelerator. You have application level concurrency, so you have several neural networks running at greater than 60 inferences per second. So you really want to deliver a very high performing subsystem. You need to worry about the real-time constraints. You need to have a preemption strategy. So when you preempt a neural network computation, how do you save the state? What is the scheduling mechanism when you're doing scheduling across multiple cores? And then how does the neural network get partitioned across the various processing units? So on the Snapdragon platform, we have the Snapdragon Neural Processing Unit. It is available for download at developer.qualcomm.com. Essentially, what it does is it allows you to exploit the heterogeneity that we have on our SoCs in order to do in order to map networks onto them. So today, what you can do is you can take the SNPE and you can map your network onto CPU, GPU, DSP. You can certainly partition your network across the various cores, and you can do your computation. It supports TensorFlow, Caffe, and Caffe2, which are sort of the most common model framework formats that are out there. We are adding support for more, and perhaps more importantly, it allows you to do optimization and debugging. So it has offline conversion tools. So if you want to convert from a 32-bit float to a fixed point network, SNPE has that. It allows you to analyze performance when you map it onto a heterogeneous platform. It certainly has sample code, and then there is ease of integration. And then ease of portability, really. I mean, so you write the application in SNPE, and every platform that we support SNPE on, you can migrate your code onto that. And that's extremely powerful mechanism. So as I mentioned, so we support the three most common formats today. We will support more in future. These are some of the networks that we have modeled in SNPE or NPE. And these are some of the applications that have been enabled using this software framework. And those applications are targeted at mobile, at smart cameras, at auto, and at AR. So in summary, there is a global massive adoption of mobile technologies, and there is a tremendous opportunity for growth in terms of AI computing requirements on the edge. Algorithmic requirements are going to be important. Techniques such as pruning, quantization, and compression will be important. So you need to look at that, certainly need to look at the networks that are being deployed on the edge. And then you really need to look at the hardware architecture and the software that will enable these networks. So that's all I have to share today. Thank you very much, and I'm open for questions.
So most of the computing and SoC conversations are happening around improving the efficiency of a single chip. But emerging network architectures like the fog, mobile ad hoc computing, and a lot of intelligence moving to the edges of the mobile networks. I don't see much of...
So what I presented today was, yes, an SoC-centric viewpoint, absolutely. I guess you're referring to federated learning and those sort of approaches, right? And certainly, I mean, so we as Qualcomm certainly understand, the wireless world quite well, right? So in terms of the hardware, what needs to do, it basically depends on the IoT device that you're talking about, right? And you will optimize the hardware in order to support what is the computation that needs to be done on one of those devices. Beyond that, you need to make sure that you have the computation capabilities in order to be able to do communication between them, right?
More importantly, the inter-device latencies in a fog.
Right.
That is not being addressed by new protocols or new approaches. When you guys are the 800-pound gorilla, if you say it has to work in 1 millisecond, it will work in 1 millisecond.
Yes, so, suffice to say, we are looking at certainly we are looking at some of those problems, right? From an R&D perspective, we are certainly looking at that. Our product roadmaps, you will have to talk to our product side in order to get an answer on that. But I can tell you from an R&D standpoint, we certainly are looking, we talk very closely with our wireless research teams on these problems. And so those are our counterparts. Really, we have a counterpart in terms of our wireless research team, and we have a counterpart in terms of the software team that we talk to in order to do the research in this area.
Thank you for the excellent talk. The question I have is started from late 80s. There has been the idea of the network of workstations. And ever since then, the connectivity has always been pointed to as the culprit because of the worldwide weight. Okay, so back then, there has been a magic number called 25 megabit per second of flow rate, continuous flow rate through the network. So do you see there's that kind of a flow rate would be sufficient for supporting the AI at the edge?
Well, it depends on what you're, the question that you're asking is really goes to the heart of how do you partition your application between the edge and the cloud, right? That's where it is going at. So obviously you have to be smart about it, right? Enabling AI on the edge helps, right? So you can basically, again, it goes back to, you can take the hierarchical computing concept that I said to the extreme. You only send something to the cloud if you think it is useful to send to the cloud. You enable inference on the edge, right? It will be extremely low power. The computation capabilities would be limited. You do the first order inference there and then only go to the cloud if you're required to, right? Again, these applications are emerging, right? And so one needs to be able to, as from a hardware standpoint, you need to have the capabilities in order to support it, which we think we do. But in terms of the application development of an application that sits across the cloud and the edge and works in perfect coherence, I think that people are still looking into that problem.
Oh, thank you.
Thank you. Thank you for your talk. The question is about how you map the algorithmic implementation like on TensorFlow directly to the hardware. Do you have tools that were able to do that, or are you familiar with companies like Bigstream, what they're doing?
So towards the last two slides in my talk, I talked about SNPE, or Snapdragon Neural Processing Engine, that can take a model which is in TensorFlow and map it onto our architecture.
But does it choose the hardware, or is it just your architecture?
You mean is SNP, it is
specific to your hardware?
Yeah, it is specific to our SoCs, absolutely. Right. So it basically allows the migration of a TensorFlow model onto our hardware, right? And not only that, I mean, to me, that's a first order support that it needs to provide. What it also allows you to do is partition your application across the heterogeneous compute capabilities that we have. So you can choose to map it onto a DSP and a GPU, or just the DSP, get feedback on performance, change the mapping if you need to, and then map that application. And you're not dealing with, the key point is, if you sort of look, if you have ever dealt with interprocessor communication, it's a lot of work if you have to go down to the low-level intrinsics to make it happen. So the SNPE is a nice layer that it provides you such that you can do the partitioning of an application across the heterogeneous platform, and all the communication is handled by it.
Okay, thank you.
Any other questions?
The three reasons that you gave for AI at the edge, you gave the reasons of latency, privacy, and reliability. So all those three reasons, I don't think they apply to doing training. So training, there's no need for training to be happening at the edge. Training can always be done on the cloud because you don't have those three constraints. So if you assume, and this is an assumption, that the training is done on the cloud and the inference is done on the edge, does it make sense for the cloud hardware to look more like the hardware that your Snapdragon hardware? So it's a combination of DSPs and GPUs, and so I know that GPU is there in the cloud, but more like what you have. So the algorithm, the software porting, what happens between training and inferencing is very, very similar. It's just on a more powerful machine on the cloud.
Right. So that's a multi-part question, really.
Yeah.
So let me first start with training on the edge, right? Or training on the edge versus training on the cloud. So in terms of privacy, one would argue actually that it's better to do training on the edge, such that I never send my private data into the cloud, which I do, in other words, I'm always in control of the data that's mine. Right?
Yeah, but training, you don't necessarily, you want to do with a lot of data, and if it's anonymized and so on, that's fine.
So that was my say. So yeah. So obviously the kind of training that you're going to do on the edge is not the same as the training that you do on the cloud, right? So the training that you would do on edge is you will take a network that has been trained on the cloud, but then is specialized to your specific needs. Right? Wherein your own private data comes into the picture, and that's the specialization that happens, and then you never send that data anywhere into the cloud. So that's one angle to it. What the other question you asked was in terms of should the server architectures or the cloud architectures look the same way as our mobile platform architectures? And the answer to that is really no, because in some ways, if you look at the reason we have the architecture that we are dealing with is because we have to address the extremely low power requirements. So we have specialization of our SoCs for different functionality, right? That argument does not necessarily, and I say, again, in some cases you could make the case, but it does not easily transfer into the server space where you don't necessarily have that tight power constraints. Right? So in that sense, the power, you don't need to have the same architecture. And the third part to your question was, I'll interpret it as follows. Hey, if you do computing in terms of 8-bit and 16-bit on the edge, shouldn't you be sort of training with 8-bit and 16-bit on the cloud? And the answer to that is yes. I think that is a lot more efficient. Right? So in other words, you do want, rather than take a 32-bit floating point network and try to fit it on the cloud, it would be better if you were to just go ahead and train it in the fixed point domain to begin with.
Okay, thank you.
Yeah, I would like to ask a question about the comparison between the CPU and the Hexagon DSP. In your slide, you just showed that DSP is almost 10%.
10x. I think it was 6 to 10x.
Yeah, 6 to 10 better than the CPU. I would like to know, in the CPU, did you guys use the ARM Neon?
I believe so. I believe it was the best implementation that was there. But
okay.
I believe that it was, yes.
Okay, good, thanks.
Hold on, one on this side.
Hi. You have architectural advances like SqueezeNet, you mentioned XORNet, where just changing the architecture, you can get sometimes multiple, 200, 300 reduction, times reduction in terms of the computation for the same level of accuracy that you had in a 200 megabyte network years ago.
Correct.
So I guess there are a lot of the things where we say, all right, well, compression helps, quantization helps, and we want to do all those things. We want matrix multiplies to be fast. But I guess the question I have for you is, what advice would you give to the people designing architectures? Say, hey, if you want this to run on an SoC with these types of constraints, you should be searching for architectures that are smaller in depth and maybe wider in terms of hidden units, or vice versa. Or what kind of, I guess, intuition do you have about the architectures we haven't discovered yet that are particularly well suited for computing on the edge?
Right. So let me preface my answer by, there's this question. I'll extend your question to begin with. I'll pose a question to myself and answer. That's what I'm trying to do here. I showed you MobileNet. I showed you, you talked about SqueezeNet. These are reducing. These are much smaller networks. They require much lower compute horsepower. They require much lesser memory. And then the question becomes, hey, have you solved the problem? Right? And my answer to that is, we are going to see a lot of these networks, a lot more of these networks. We are just, in my opinion, we are just starting this trend of applying neural networks to computing on the edge. We are going to see a proliferation of these approaches across many different applications. At any given point in time, you will have multiple networks that would be running onto your device. And because you will have these multiple concurrent use cases at hand, you will, even though the network architecture size has reduced, you will require the horsepower that is there. So that was the first point that I wanted to make in the context of, okay, the sizes are reducing. Now in terms of the question, okay, what should the network architecture look like? I would certainly say reducing the number of flops required per inference is important, because that you know, in the end of the day, you want higher inferences per second. So if you can reduce that, that certainly helps. Reducing the memory footprint is extremely important, because that saves you on the DDR power. Those are 2 points that I made in the talk. The third point I will try to make is that certainly looking at the precision of the network up front, right? Not waiting, you know, not training it in 32-bit floating point and then migrating towards 8-bit or 4-bit. So I would say if there are architects, if you see you can migrate it to 4-bit, there is an architecture that is out there that does it in 4-bit, then design it for that. I believe there is a dependence between what is the architecture of the network and what is the precision that you use for the weights. I think typically that doesn't get addressed, right? You typically do it with 32-bit floating point, the architecture remains fixed, and then you do the retraining on it. So I think breaking that cycle and looking at lower precision to begin with, and this devising architecture for lower precision, I think that will be helpful too.
So we have time for one more question. So that's the last one.
A quick question I had is regarding your always-on situation that you mentioned for wearables and potentially mobile devices. I anticipate most of the use cases are going to be before the OS is pretty much active. So you wake up your system from your deep sleep state and the OS gets active. So I anticipate your software enabling strategy specifically for always on is going to be very different than what you have on your streaming or an active state. Can you put your thought on that?
So essentially it goes across. So let me answer it in parts. So first of all, if you're going to be mapping a neural network in that to your always-on subsystem, sensor subsystem, then certainly SNPE can help you, right? But what you're raising is a slightly different question. What you're raising is, okay, I have that subsystem, and then that subsystem is going to wake up a more powerful subsystem, and then that's also going to be running in another neural network, right, with a higher accuracy. So in that case also there will be an SNPE subsystem which will allow you to do that. Now the key question is, how does this, what's the mechanism to wake up, to go from the sensor island subsystem to the higher performing subsystem? And then we have intrinsics that allow you to do that, right? And it is outside the SNPE fold in that sense. So it is not, whether SNPE does not really necessarily enable that, but we certainly have software intrinsics that allow you to do that.
Okay, thank you.
Okay, let's thank our speaker one more time
Thank
for
you.
the excellent talk. Do you have the clicker? Yeah, that's fine. Okay. So we heard a lot of real-world applications from the wireless and mobile leader Qualcomm. So session 1 we covered research side and the mobile computing side at the edge. And in session 2 we will hear from Intel and AMD on the cloud side for computing in cloud, and Dr. Ali Kashavarzi will moderate the session. So I think we're done with session 1. We go for the dinner break and networking in the cafeteria. For logistics, we sent you the map last night in the email, so you should have received the map. Basically, you go, so we take a break for 1 hour. We have to be back by 6 p.m. for the session 2 of the hardware. And if you guys have the map, you go through the middle door in the lobby, you go straight, and to your left, you find restrooms and also cafeteria. But the IEEE dinner is in the back of the cafeteria, so you have to walk all the way to the back of the cafeteria to find the dinner. But you see the sign. Thank you very much. Please start coming back 5 or 10 minutes to 6 p.m. so we can make sure that we start right at 6 p.m. Thank you very much.